Thank you. So first, I would like to thanks a lot the organizer of the semester. It has been a great pleasure so far. The conferences were very nice, and the rest of the time it was also very nice. So I'm going to talk about a joint work with Alex and Andrew. But in fact, during the first half part of the talk, I will try to kind of convince you of the general behavior of a whole family of processes. This is going to be quite heuristic. It's not going to be extremely rigorous, and actually, I'm not even going to give you a precise set of assumptions. And then in the second part of the talk, I will explain a result which kind of show that for some specific cases, let's say, we are able to actually show this behavior. And also, I will try to convince you why actually this model that we look at do enter in this kind of broad family of process that I want to consider now. So essentially, the process that we want to look at, let's say that for some preliminary heuristic reasons, we are able to deduce that they should satisfy an equation that looks like dxt is equal to xt to the power minus beta. The reason why I put a minus sign here will become clear later, but beta is not specifically positive or negative. dt, and we'll get some error term, some kind of fluctuation term, or I don't know. I'm going to call it RT. You can think of it as being a Brownian motion. But in fact, you can consider very broadly pretty much anything which has roughly IID increments. Is that big enough? Yeah. So roughly IID increments with finite variance, the increments. And zero average. And by roughly IID, what I mean here is pretty much that by roughly independent, I mean essentially that there is no long range correlation between these increments. And by roughly identically distributed, I essentially mean that as t goes large, these increments do not go towards zero and they do not blow up. They remain of essentially of order one. So zero average. So martingale would work. Martingale would work provided that your sigma is essentially bounded and bounded from below. And also, actually, you would need that that you say if you were to consider a diffusion that would be sigma of x dw, for example, you would need that sigma actually converge as x goes large. But once again, I do not want to be too precise. And in fact, I think the only case, well, apart from the example, I mean, the situation I will give later, the only situation where I'm able to fully justify everything here is essentially the case where it's just a Brownian motion. But yeah, we'll see that later. So in particular, with this assumption, there is one thing that you should expect is that RT is of order about square root of t, by which I mean that the lim sup of log R t divided by log t is equal to 1/2. Okay. Okay, so what can we do with that? So essentially, our goal is to study the behavior as t is large of this equation. We are mostly going to consider a situation where, in fact, it will turn out that xt goes toward plus infinity. So in fact, I do not really want to mind too much about what's happening when xt is close to 0. So here you can see that as xt goes to 0, you might have a blow up, so you need something that regularizes it. you want to think that, in fact, you do not have a blow-up as xt goes to 0. Okay. So the first thing we can do is to look at the equation without noise. And already we can see that there is some interesting behavior and that we have some kind of phase transition depending on the value of beta. So if we look at dxt equal xt to the minus beta dt, we can see that, well, of course, we can solve that very explicitly, and that's very easy. For beta equal -1, we get that dxt over xt, which of course is d log t, log xt, sorry, is equal to dt. So if we take, for example, the initial condition that x0 is 1, then xt is just exponential. So we have exponential divergence. Okay, that's good. Now for beta, that is different from -1. You similarly get, so you multiply by xt to the beta. And this, of course, is 1 over 1 plus beta, d of x, 1 plus beta, t. And so you get, say, with the same condition that x0 is 1, what do you get? You get xt, the 1 plus beta is equal to x0, which is 1, to the power 1 plus beta, plus 1 plus beta, t. Okay, so you take the power 1 over 1 plus beta, and what you see is that for beta below -1, this is negative, and this is negative as well. So what's happening is that because this is negative, there is a finite t such that this is 0, and then since the exponent is negative, that means that you have blow up in finite time. So what's happening above -1? So above -1, this exponent is positive, this is positive, and so you see that asymptotically, you just get 1 plus beta to the 1 over 1 plus beta times t to the power 1 over 1 plus beta. Okay. So here what you get is xt equivalent, let's say, of the order of t to the 1 plus beta, 1 over 1 plus beta. Okay, so now the next question is what happens when we actually do have the noise? Is this like deterministic approximation even good at all? And what's happening is that it is the case below 1. So we have a second critical point at beta equal 1. When you above 1, you can really see that this cannot be a good approximation at all. The reason is that above this value, this is much smaller than square root of t. And just by a very simple inequality from this equation, you see that xt, well, say, apart from maybe the value at 0, is bigger than RT. And since R is can take the value as large as square root of t, you have no chance that xt is going to be of an order smaller than square root of t, right? So in fact, what's happening here is that x is diffusive. Okay, so you can show that this induces that the limit of log x over log t is going to be at least 1/2, just because of this. Okay, and in fact, you can show that that it is an equality, the mild assumption It's essentially because of Gilsonov theorem. Essentially, what's happening is that when xt is much bigger than square root of t, these drifts become essentially irrelevant. The power here is negative for beta bigger than 1. So this drift is not doing much. And so the only thing that is pushing you is your thing that looks like a Brownian motion. And so there is no chance that you will go much above square root of t. Okay, and in fact, you can show that in this window between -1 and 1, it is the case that this is of order t to the 1/1 plus beta. In the case that we have a Brownian motion here, this follows from Gratienaro and Offret. Okay, but I want to give you some intuition. Also, it's far from a rigorous proof. So okay, so the idea is that okay, I do. Yeah. Yeah, so in Gratienaro and Offret here, you can have some power of t as well, I believe, some stuff like this.
X times sine of t. Something like this.
Okay, so essentially the idea is you want again to multiply, as in the deterministic case, you want to multiply by xt to the beta. You integrate. Okay, and that gives you something. What does it give you? That gives you that xt to the beta dxt is equal to dt plus xt to the beta drt, which you now want to integrate. And I'm gonna do something that, of course, we cannot do. I'm gonna completely neglect the quadratic variation part. So I'm gonna pretend that this is the same as d of xt 1 plus beta divided by 1 plus beta. The reason is that if I were to put a quadratic variation term, then that would mean that I assume that R is essentially a martingale, which I do not want to do, actually. In fact, I want to have in mind here really something that have the same large range behavior as a Brownian motion, but which has a very different small scale behavior. In particular, I want to think some process which have a finite, which have a zero zero quadratic variation. But of course, here you can turn this into something rigorous, add your quadratic variation term. You need to do something about what's happening at 0. So, for example, consider only the event that xt do not hit 0. Okay, and so when you integrate, you obtain that xt to the 1 plus beta is equal to 1 plus beta. And then you get here t plus the integral from 0 to t of xs to the beta drt. And I'm just going to take the power 1/1 plus epsilon, but I'm not taking into account the value at 0 here. So it's actually, I should have here plus a small O of 1 inside the parenthesis, which is just the big O of 1, sorry, which is just the value at 0. Okay, and now I'm gonna put the t out. because this is here we recognize our behavior if there was no no stochastic term. And what we get is 1 plus the average from 0 to t of this. Although I should not call it an average of all. Oh, I cannot. Okay, so basically one thing that you can do now is that instead of using this equation to show that you have such an asymptotic, you can be a little bit stupid and do it the other way around. You assume that you have such an asymptotic behavior, and you want to know whether this is coherent. So you want to feed back this this asymptotic into this equation and see whether it is the case that this is a small O of 1. In which case, that would mean that indeed the deterministic estimation is correct. And in fact, in general, this, but once again, at a heuristic level, this reversing the implication works pretty well for differential equation. And basically, when you get something coherent, it generally means that you can actually apply Grunwald lemma and actually show that that this is not much more than this order and also not much less. Okay, so what's happened if you try to feedback this into this equation? Well, the first thing is that you need to be a bit careful because this is an asymptotic estimation that is true for large t. And it's not clear in the first place whether I can use it for small t. So the question here, so I would like essentially to say that this is about the same thing as 1 over t integral from 0 to t of s to the power beta over 1 plus beta drs. But for this, I need at least one thing, which is that this integral, but from 0 to infinity, is infinite. Because if you take this integral from 0 to infinity and you get something finite, then this from 0 to infinity is also probably going to be something finite. And so this thing is going to converge toward the constant, this is going to converge toward the constant, but they have no reason to be the same. So then in that case, this asymptotic estimation will be bad. On the other hand, if this integral is infinite, then you can use this asymptotic estimation. So here we have essentially it's my first short board in ages, and I have no idea how to deal with these boards. Okay. So here we have a question, which is it the case that the integral from 0 to infinity of, well, xs to the beta, but you can actually use the other one. You can use t to the beta over 1 plus beta drt is finite. And the thing is that you actually do have different behaviors depending on whether this, this integral is finite or not. And that gives you a third point, which is the value of beta equal minus a third, where you will get different behaviors above and below. But these different behaviors, you will not see them in the first order asymptotic, but in the second order asymptotic. So what I'm saying essentially is that in this window, I think it's time to erase some things. In the window in between -1 to minus a third, you should expect that this integral is finite. And it follows from it, in fact, that xt is going to be equal to a constant. Okay, so this is just the deterministic approximation. You will get a second order approximation, which is another constant. And you will get this integral. Place a small o of t to the 1 plus beta minus 1. And in fact, the value beta equal minus a third is the value where this exponent is square root of t. And below this, you will get indeed that xt is going to be given by the same constant here. And then you will get some central limit theorem. So you will get essentially a square root of t times a Gaussian. Now, I want to emphasize that these behaviors are not only very different in this power of t, but also in the fact that here it's a strong convergence. This is just a well-defined, like, finite quantity, and you will get almost through estimation. And here, you can certainly not expect almost through convergence, because basically, if you look at this as a function of t, then what you will get is here in essentially a Brownian motion. Okay, so a way to think about this is really to think, in the case R is a Brownian motion, what I have here is a martingale from, if I take it from 0 to some t, as a function of t, it's a martingale. And then it's a question of, is this martingale bounded or not? And if I have a bounded martingale, I will converge toward my martingale, and otherwise I will have some central limit theorem. Yes. So once again, I'm neglecting the, so okay, let's I think I've erased the equation. So yeah, you want to neglect what's happening at 0. One way to deal with this is to actually look at xt max 1, if you want. To the minus beta, yeah, bt plus 1. So I just, yeah, so actually you want to think of this as the asymptotic behavior when x is large. You want to think that this is like a, so from my point of view, this is not even like the equation that you start with. This is really, you start with some model, and by intuitive reasoning, you deduce that for large x, your x should look like this. But also in the end, you will get, so even for beta negative, what you will get is that x is going to blow up toward plus infinity. So in fact, you could look at this, say for Brownian motion, you could look at this with an initial condition which is positive, say 1, and only look at the event which has positive probability that x never reaches 0. Yeah, yeah. Yeah, I'm really thinking about the situation, yeah, let's say the situation where you never hit 0. Okay. Okay. So sorry, no, I'm lost. Okay, so just to justify this behavior in the situation where you're working with a Brownian motion, and let's not forget that we removed the term which is the product variation term. There is a product variation term that we completely ignored. So in fact, if you want to do it rigorously with the Brownian motion, you have to take into account this extra quadratic variation term, but it's rather easy to do. So if you have this, you know, in fact, that this is a martingale. And so if you want to know if this is a small O of 1, you know that you just need to look at the quadratic variation of this martingale. Your quadratic variation is integral from 0 to t of s to the 2 beta over 1 plus beta ds. And so your question then is it the case that 1 over t times this integral, is it the case that this integral from 0 to infinity is finite? And here you can see that this is just equivalent to 2 beta over 1 plus beta being smaller than -1, giving you 2 beta smaller than -1 minus beta. You add beta on both sides, and you do get the condition that beta is less than minus a third. And in the case when this is infinite, in the case when this integral is infinite, what you get is that the quadratic variation of this is about this quantity, but up to t. And this is of order t to the 2 beta over 1 plus beta plus 1. So this is going to be your quadratic variation. So this thing is going to be of the order of the square root of that. And then you multiply by 1 over t. So you're losing 1 power of t. And so that will give you that this term is of that order, which is t to the beta over 1 plus beta minus a half. In this range, this exponent is going to be less than 0. And so this asymptotic estimation is correct. And when you want to get a second order estimation, you can now take an expansion of this, so you can drop the exponent. And that gives you that this is the main order of the correction. Okay. And then when you multiply by this t to the 1 over 1 plus beta, you do recover the power square root of t. Okay. So now it's time to actually talk about the model that we look at in the paper. So it's a model of Brownian motion with reflection. So this I want to keep. So the model is the following. We have a domain which may look either like this or like this. So the set of couple xy, this is the x direction. Let's say that 0 is here. So x is positive. In this direction, we actually have d dimensions when n plus times rd. And the domain is given. So here we can see symmetric. We can see symmetry, but it's actually a rotational symmetry. So it's actually given by the condition that the norm of y is smaller than some function of x. Okay. So we're gonna have a Brownian motion constraint in this domain. The function bx is assumed to be equivalent to x to some power beta with no minus sign this time. And we can have a multiplicative constant in front of it. And our equation for the reflection is given by dz, that is our process, is, okay, let's say dw plus some local time correction multiplied by some vector field. So we can actually add some sigma matrix. We do not need to consider here Brownian motion. And the conditions are essentially that this vector field V is pushing positively in the x direction. And we want it to, in some sense, to stabilize, by which I mean that if you look at, well, you want a point in the boundary of that domain, a point in the boundary of that domain is of the form x, b of x, u, where u is a unit vector in Rd. And you want that this converges as x goes to infinity towards some limiting vector field. And this limiting vector field, you want that it has a positive component in the x direction. Sorry, how do we write a scalar product? Okay. And in fact, you want it to be independent from u. The sigma matrix, you also want that it converges toward a matrix that do not depend on anything. And then, because we will want to get asymptotic behavior below the first order, we need quite a bunch of technical assumptions. The reason being that, for example, if I take bx, that is x to the beta, but then I add some correction, which is, say, some power that is almost beta, then it's sure that this is going to give me corrections that are going to be like in between this exponent and this exponent. So if you want to avoid this extra correction, you need basically that not only that this is equivalent to your x to the beta, but you want that this asymptotic estimation is good enough. So you want essentially that this is this plus a small o of a nice enough power of x. Okay. And there is similar assumptions also for V and for sigma. And then we can show that exactly this behavior happens for beta in between -1/3 and 1. And also that actually this behavior cannot happen below -1, -2/3. So there really is a transition at -1/3. It's not superficial. It's not that we are only able to treat this case, is that this is false below -1/3. Okay. So here the result essentially is that so let x be the first component of this process z. So z is equal to x, y. This one is one-dimensional, this one is d-dimensional. Okay, so we can show essentially that for beta in between -1/3 and 1, there exist two constants, C1 and I want something for volatility that would not be sigma. Let's call it S. So minus C1 t to the 1 over 1 plus beta divided by square root of t converges in distribution towards a Gaussian. The first order asymptotic, that is this behavior, is the fact that this is equivalent to this, is true in between -1 and 1. This is a result by Misha, Aleksandar, and Andrew. Also, the fact that we do have the explosion by below -1 and that there is a diffusive behavior above 1 is a result of them. Okay, and here we have this. And furthermore, this cannot be true for beta below -1/3. And the reason is essentially that it is possible to couple two copies of this process. So to have xt and say x prime t, two copies of the same process, such that the distance, well, between xt and x prime t is much more than square root of t. It's actually 1 over 1 plus beta minus 1, which for beta smaller than -1/3 is much bigger than square root of t with positive probability. It's x prime. That these are just like two copies of the same process. Okay, so I have like z and z prime that both satisfy this equation with different Brownian motion, let's say. Yeah, well, it's actually easier to do it like by considering different starting points. But yeah, you could do it with the same starting point. No, not with independent Brownian motions. The Brownian motions are coupled in a clever way. So essentially the way it works is that you want to, no, sorry, we are below -1/3, so below 0, so it looks like this. And essentially what you do is, okay, let's say you start with different points and you take them to be, so that they meet at some point, and then you drive them with the same Brownian motion. But the thing is that they do not arrive here at the same time. One arrive at some time t0, the other one arrive at some time t1. Yes, but it's because it's not the same time. So basically what happened is that you get that xt is equal to x t plus s, x prime, sorry, of t plus s. And since you know that xt is t to the 1 over 1 plus beta, and this one is c t plus s, the 1 over 1 plus beta, basically the error here that you commit by having a s that is not 0 is already of this order. That's essentially what's happening. And so it is the case that that xt minus x prime t, well, this is actually just going to be xt minus x t plus s. And this is going to be indeed much bigger than square root of t. Okay, so what's happening here in below -1/3, basically, you are extremely sensitive. You are sensitive to your initial condition. You are sensitive to what's happening in finite time. Yes. So okay. So if you have something like this, you can conclude indeed that that this is not possible. So let's say that with this happens with a probability P. Basically, if this were to happen, you could cut your Gaussian in such a way that below, like in this area, you have a probability that is say less than P over 3. And you see that it's not possible, that both X and X prime satisfy this, because there is an event of probability P such that they are very different, but there is only a probability 2P over 3, which is less than P, that they are like in this area. And if they are both in this area, then they cannot be far away. I'm saying if they are, this is some constant. And so if they are both in this area, the Gaussian here, basically that means that you have a distance that is of order square root of T between them. Okay. Okay, so the last thing I'd like to do, if I have time, yeah, is to actually explain why it's the case that this is in the this system should be in the first class of equation, because I don't think it's clear at all. So I'm saying you take this system, why would it be the case that the X component will be approximately equal to X to the beta dt plus some just correction terms? Okay, so this part of the process, you can actually just put in the correction. So this one is not trouble. The question is, why is it that this would be well approximated by this? So what I'm saying is, let's look at the local time. Okay, so I'm gonna, for this explanation, I will assume that beta is bigger than 0. It's just because otherwise it's a bit more complicated, but you can modify the argument so that it works. So let's assume beta is positive, and let's look at the local time at t plus 1 minus the local time at t. And what I would like to say, essentially, yeah, okay, no, let's first look at this. So I'm saying this, in fact, is going to be 0 with large probability. Provided that t is large. And in the case it's not going to be 0, it's going to be approximately 1, the order of 1. And this is going to happen with probability, which is approximately xt to the minus beta. So the reason for that is that when you take a slice, you are at xt, you take a slice at xt in the, so you take a slice x equal xt, and what you see is just a ball, a d-dimensional ball. So you have your ball, its radius is b of xt. And you have your process, which starts somewhere in this ball, and then it runs for time 1. Your sigma matrix is about 1, so you know that it's going to move by the distance of order 1. So if you want the local time to be not 0, it needs to start pretty close from the boundary. It needs to start at a distance of order 1 from the boundary. So you have a distance here, which is of order 1, and I'm essentially saying that this is going to be of order 1 exactly if I start in this area. Well, that's very roughly. But so the question is, what is the probability that my Y process is in this area? So in fact, you can show, well, that's a big part of the proof, but you can show that the process Y probably not, properly normalized by b of xt, so that it's something on the unit disk. It will converge in distribution, and the invariant distribution satisfies some PDE with reflection, not with killing, And in particular, this invariant measure will have a density with respect to the Lebesgue measure, and that density is not going to go towards 0 near the boundary, and it's also not going to explode. It's going to be essentially constant. So the probability that that you end up in this area is in fact of the same order or as the relative area of this set. Okay, so I'm saying the probability that LT plus 1 minus LT is different from 0, it is roughly the probability that YT in norm is in between BXT minus 1 and BXT. And I'm saying this is roughly the area of that set divided by the area of the ball. The area of that set is B of XT to the power D minus 1 times some constant. And the area of the ball is BXT to the power D. So this is about 1 over BXT. And this is because of the first order asymptotic. We know that this is of the order XT. No, sorry, not even because of the asymptotic, just because of the behavior of beta, of the function B. This is about XT to the minus beta. And so what you get is that LT plus 1 minus LT is going to be 1 with this probability roughly and 0 otherwise. So if you now take an S, which is kind of large, but not that large compared to T, this will average out. And so it's going to be approximately the same as its expectation. It's going to be about the same as its expectation. And so its expectation is going to be S times the probability that LT plus 1 minus LT is different from 0. So that's going to be about S times XT to the minus beta. And so you have an increment in a time horizon S, which is large but not so large, which is going to be about this. And so this is why this is at the very first order well approximated by this, well times the constant. Okay, thank you very much. I hope it was clear enough. I'm waiting for your questions.
Increment and approximately the variance. So behavior of this vertical coordinate divided by horizontal is approximately like Bessel process. It's approximately like Bessel process. And if you are close to the boundary, then you have this. But if you are at the center of ball, you have at first to reach the boundary and then to accumulate this local time.
Yes.
How do you calculate the probability that Y? So do you have something in your calculation that explains the time span outside of this full life?
So, okay, so let's say that you look at the process A, you fix some capital T, and you look at the process AT, which is Y T plus T divided by Bx T plus T. So the first thing is that the finite time, say, variation of this process are much larger than this one. So in fact, this is about the same as Y T plus T divided by Bxt. So, sorry, I think this is too complicated. Essentially, what I'm saying is you have your domain like this. What you do is you look at some window around your point ZT. This window is going to be in this direction of order B of XT. But in this direction, you can actually take something that is much larger. and but not so much. And when you rescale things properly, what you're seeing here is essentially a diffusion on the infinite cylinder, right? And so here, what's happening is that y is going to reach equilibrium much before this varies. And so much before like x varies like by a significant amount. So essentially, you first show that y reaches some invariant measure. The invariant measure is just the one that is given by diffusion on the ball with your matrix sigma and like with your reflection vector field, or projected, but that doesn't really matter. And so here you just have a just like casual problem, and you know that you have an invariant measure and such. I do not really, in the calculation, show anything like really like this, I believe. Yeah, sorry. Yeah.
But to calculate the variance, so you have to subtract expectation, t times expectation with respect to state. But then limiting sigma squared is like integral from negative infinity to positive infinity, some correlation between two points.
So is your question about the error between this and this, essentially?
With respect to stationary variable.
Yeah, I don't know. I'm not sure I understand what you're saying. Sorry. Maybe you can discuss this later.
I don't.
So, well, I think it has to do with the use of Lyapunov function and the fact that in the end you find some nice functional which allows you to not study that much the local time directly. So for this part, it's actually very related to how you get the first order behavior. So maybe your answer is already in the paper about the first order behavior. I don't know. Yeah. Yeah, sorry, I don't have a convincing.
So there's a semi-physical situation where the gravity has bias, so you have a rotational symmetric cone or something like that in some type of potential.
Yeah, so the case of the cone would correspond to having essentially beta equal 1. So here you get something that that becomes much smaller compared to a cone. The Brownian motion is inside, but when it's so basically when it's inside the domain, it does not fill at all the vector field, so the one that you're calling the potential. It's only just a Brownian motion, well, with a sigma matrix if you want, but it's a Brownian motion, let's say. And only when it arrives to the boundary, the local time is pushing it inside. But instead of just pushing it like it would usually do, it's like it translates it like even so slightly, kind of. Yeah. To force your Brownian motion to stay inside that domain.